Good morning, good afternoon, or good evening to everyone everywhere. I'm Marcin Rojek, co-founder of byteLAKE, and together with my friend Robert Daigle, who is AI innovation and business leader at Lenovo, we'll talk about AI federated learning. We'll explain how this technology is bringing collaborative learning and privacy together to the so-called edge devices. We'll talk about edge devices and what benefits they bring, and specifically in the context of federated learning, what you can expect and what this technology can bring across a number of industries. Usually at this moment in time, we say something about energizing crowd in stands or in front of us, but since we're doing this presentation online, I can only say once again, warm welcome to the AI federated learning presentation.
Thank you so much, Marcin. We're so glad you're all able to join us here today virtually at the Federated Learning Conference. And we know that if you're here at the conference, you probably have a good understanding of AI, but we wanted to just recap some basic terminology that I think will be important and relevant later in our presentation. So artificial intelligence is defined as a program able to perform tasks normally associated with human intelligence. Another definition of AI that I really like is it's when a computer does something you wouldn't expect it to do. Now, machine learning has been around for quite some time, and that's when a program can perform a task without explicit programming. That, for example, when a computer can make decisions based on new information without using things like if-then statements, and it's actually doing it based off of a learned pattern in the data. Now, the more emerging area of machine learning that there's been a lot of work over the past few years in is deep learning. And that's when a program uses artificial neural networks to learn patterns in the data. And it works similar to how the human brain learns new patterns and new information. And so with deep learning, the key here is that it requires a lot more data and it's much more compute intensive than traditional machine learning. Now, you probably hear about NLP and computer vision and robotics in association with AI, and those are really more about the core capabilities that you can apply artificial intelligence to. Things like computer vision, where you're learning patterns in image data or visual data, whether it's image segmentation or image classification. The other part I think that's important to cover in artificial intelligence is the difference between training and inferencing. And this is really key for enterprises because you're not just, creating a model in the lab and research and development, but you actually have to operationalize your AI project, your AI initiative to drive some business value. A few trends that we see coming from this adoption of enterprise AI is the increase in inferencing at the edge. It's moving the compute closer to the data source. Also, the computational intensive nature of deep learning is driving up the demand for compute and accelerated computing, as well as the need for real-time low latency inferencing. So when we start, breaking down the market, and I think this is important for understanding the timing, right, for these new trends like federated learning, as understanding really where the market's at today. What we've seen over the past few years is really the innovators that are out in front and are developing a lot of the core capabilities for AI. A lot of this is driven by the cloud providers, the large CSPs, and they're developing and really driving the whole ecosystem forward, and major contributors to the open source community, for example. So really they're moving the market forward. Research that includes high performance computing and universities and academia, and emerging technology. And this is really kind of a group that we've bucketed to talk about all of the tech firms that are really AI-based companies. Really, we see them as really on the forefront of the market. But what we've seen here is that there's a lot of focus on training and building models and moving the market forward. But what's driving this next wave is really the adoption within the enterprise. And what's interesting here is that's what's really becoming the catalyst for things like real-time analytics and for edge AI. When we look at the enterprise market, to give some idea of where it's at today, it's still early on, about 18% in production, 31% are in some type of POC, and about 51% have not started their AI initiatives. But this is rapidly changing, and so across enterprise, to drill down into the enterprise market a little bit more, we actually see that there are some leading industries that are the primary adopters, and there's good reason for that. There's external paradigms happening within these industries that are putting a lot of pressure on driving efficiencies and improving things like customer service or consumer services. So we really see these external factors really moving the market forward. If we look across the top 4 industries, over half of AI use cases are really attributed to just 4 industries. And if we break those down, and there's a lot of different use cases, but if we just look at the leading ones, here are some of the examples. In manufacturing, predictive maintenance is a leading example of how AI is being used in manufacturing to improve machine uptime, which is a significant challenge for manufacturing industry. Quality control, visual inspection, so being able to catch defects and quality issues before parts leave the factory allows you to reduce your field support cost and reduce that significantly. Also improve the customer experience, that they don't end up with a defective product on arrival. In retail, loss prevention is a key use case, and that's actually an application for computer vision and applying AI to prevent and reduce the amount of shrinkage in retail environments. Logistics, either back office or in the store, in the front of store, things like shelf restocking in the front of store, and then supply chain logistics in the back office are really important for retailers. And then also just analytics, being able to understand the customer journey in the store the same way you do on an e-commerce site, being able to see their journey and improve the experience in the store, and being able to measure that. And that really hasn't been possible without some of the new advances in computer vision that we're seeing. Finance and healthcare are another area that we're seeing a lot of work being done in AI. Maybe a little bit slower because some of the regulatory constraints here, but still a lot of adoption of machine learning and deep learning in these 2 areas. Things like credit decision and risk management, fraud detection, threat intelligence, and algorithmic trading in finance. And in healthcare, medical imaging and medical image diagnostics, being able to review things like CT scans and prioritize them for physicians, things like clinical decision support, to put the resources of research at the hands of more physicians, and even things like customer service is really important for the healthcare industry. And Marcin, byteLAKE's been doing a lot of work in these areas. Can you share a little bit of your experience across some of these key verticals?
Yeah, absolutely, Robert. So I would start with manufacturing. We've been recently working heavily on bringing digital twin concept to the computational fluid dynamics area. And that's very exciting research where we actually leverage AI, deep learning, to accelerate, to significantly reduce the time of industrial simulations. So think of instead of running your typical, be it open foam CFD simulation, which might take something between 4 hours, 8 hours, and we've seen examples where those simulations were running for 2 weeks. you can get the results within minutes, or in some cases even within seconds. This level of speed up also introduces a number of new possibilities where you can cut down on the number of trial and errors simulations, or you can run more efficiently your inverted design approach. So think of use cases like when you design aerodynamics for a truck, or when you want to simulate some chemicals mixing for pharma industries, you can run a lot more simulations within the same time and utilizing less resources. Talking about healthcare, a very exciting case for edge AI, something we will talk about more in a bit. Here we've been working on building a device that can process sound in real time and provide some additional analytics for doctors and to enable new features for devices. As Robert said, retail is probably one of those industries that will benefit mostly from technologies called machine vision or computer vision. And here we're working on bringing intelligence to hotels industry, or in general to hospitality, which can be very well applied also to the retail industry, where you use computer vision or intelligent cameras to analyze the situation in the shop, provide some analytics, and enable things like automated checkout or improved self-service to detect what you have on the plate, prepare the bill automatically, or to just provide the analytics for your restaurant or a chain of restaurants. Yeah, so number of exciting use cases.
Thanks, Marcin. And I think that's really good context to see how it's being applied. You know, I think real world examples are always great ways to kind of showcase how technology in general is transforming industries and why it's relevant, and especially in the area of artificial intelligence. And really, what we've seen, and this is kind of my view of the evolution of enterprise AI over the past few years, we've seen really the work in deep learning really move the market forward and drive adoption for artificial intelligence. And also that we talked about earlier is the advances in computing as well, to be able to train deep neural networks, things like GPUs and accelerators that are becoming more accessible and proliferating the data center, but also seeing that move to the edge. You know, as we see enterprises start adopting AI, what's different about the enterprise is that you need to drive some business value out of it. And that means you have to actually operationalize it. It can't just stay in a research state, but it actually has to drive value for the business. And what we're seeing there is, as more organizations start operationalizing AI projects, we're actually seeing more demand for the compute to be closer to the edge, closer to where the data sources are. Of course, this is especially true in areas where you're trying to do real-time analytics. And we've seen a lot of work because of some of the things that have happened in deep learning recently. We've seen a lot of work in computer vision and visual analytics that has really driven the demand for greater compute power at the edge. And really, when we're talking about edge AI, we're talking about being able to run inferencing models and even train models at the edge. And I think the next wave of that is federated learning. As we start becoming more sophisticated with our models that we're deploying, we start optimizing not just the models, but our compute, our IT cost, all of the things surrounding the deployment of it. We'll look at security, we'll look at network bandwidth that's being consumed, and we'll also look at time to deploy. And those type of factors start coming into play as you become more sophisticated with deploying your AI projects. And that really primes the stage for federated learning. And here's a few data points that I want to share with you to give you some insight on where we think the market's going to go. For edge AI, around 28% to 30% of AI hardware will be at the edge by 2025. A lot of this is going to be inference to start out with, but we actually think that as federated learning becomes utilized, that we'll actually see that become a mix of inference and training. IoT data. So we have kind of this explosion of IoT data, and there's a close relationship between IoT and AI, because really the only way to make sense of these mountains of data that are being generated, and it's an exponential curve of data being generated by IoT devices, it's not possible to analyze all of it by humans. You have to look at machine learning and deep learning to analyze that data. We're talking about 41 million devices connected by 2025, and that's going to generate about 79 zettabytes of data. That is nearly half of the global data sphere by 2025 is going to be generated. The data is going to be generated by devices. So these are paradigms that are coming that I think are going to accelerate the adoption of edge AI, which we see those deployments today. We're already there today with edge AI and real-time analytics, and is going to accelerate our adoption of things like federated learning.
You said 79 zettabytes of data. It's probably beyond my comprehension right now. I can't even imagine what that would be, right? I can imagine like maybe 8K videos or maybe sound, maybe recording the data from 360 cameras, or maybe explosions of sensors across your Industry 4.0 factories, and the number of various types of data, right? The exciting thing about this decentralized or distributed data is actually that most of this data is or will be born at the edge. So what is edge AI? In short, or in principle, it's about running algorithms or AI models directly on your device. We call it AI inferencing. So think of use cases like, for instance, intelligent cameras that can run algorithms directly on the devices that are either connected closely to the cameras or on hardware accelerators that are being part of the embedded system wrapped up under the whole system of camera. And then you can use this camera and the algorithms to detect shapes, patterns, which then leads you to use cases like automated manufacturing analytics or quality inspection or detecting some abnormal behaviors on your production line. Then you can connect a number of embedded devices to your IoT sensors, measuring humidity, viscosity, dust level, temperature across your whole factory, and then analyze the data on the spot and make the decisions. So the clear benefit and immediate result of having AI close to where the data is actually captured is that you can process the data almost or even in real time. You can trigger the alarm, you can provide the results like the shape is detected, maybe some error on production line is detected, a number of things like that. That leads us to another benefit of edge AI, which is reduced bandwidth needs. So think of a use case where in the past you had to send over the whole stream of data produced by a camera, for instance, to the server. And then in that turn, you waited for the results and then presented it somewhere in your BI system. Nowadays, you don't need to send the whole raw data, you just send the results. So it could be like number of people in a factory, just sending a text data, a number, right? Or it could be another thing like triggering an alarm or a signal that you can send to another device, and then it can be processed there, for instance, in the manufacturing quality controlling systems. So AI on edge is all about doing the standard AI stuff, like analyzing text, image, video, sound, or time series data, what have you there, but it's happening directly on the devices. Few things we need to consider when designing such devices are, obviously, the algorithms need to be highly optimized, because the number of resources available on those constrained devices like camera or small embedded systems are quite limited comparing to the cloud ecosystem or to your data center capabilities. So you have lower memory amount, you have lower compute capabilities, And these things need to be taken into account when designing, for instance, object detection in your real-time video. Another thing very important here is energy consumption. You cannot just perhaps process the whole data that you get from your camera. You need to implement a number of tricks like processing every other frame, or maybe limiting the number of data that is stored on your device for real-time processing, and send some additional using other channels for advanced analytics to your server. To sum up the benefits of Edge AI, so as I said, enables scalability. And that really comes down to decentralizing AI algorithms or models across your whole infrastructure within a factory, or across different medical practices, or across your devices that need real-time responsiveness. Another benefit is enables real-time AI experience. So as we process the data almost at the place where they're captured, we can analyze them in real time and produce the results. Then we don't need to rely that much on the bandwidth. So imagine the use case of Factory 4.0, where you deploy the cameras to analyze the production line quality, or detect some errors happening there. Imagine what bandwidth you would have to provide across your whole chain of factories to be able to send over the huge amount of videos in real time to some kind of servers, and then process it on the server side. With Edge AI, you can just analyze the frames or every other frame directly on the camera. That also eliminates issues with intermittent connectivity, which is not a rare condition for industrial cases, where whether the bandwidth is not enough, or might be not enough, or we lack it at all. Reduce the total cost of ownership. Then we don't, with Edge AI, all of a sudden we don't need to store the whole data somewhere in our local storage or in the cloud. We can just process every other frame, or for instance, for sound, we can analyze the data on the spot. And there are other use cases that are very applicable for Edge AI. Sometimes AI is as relevant as it can provide results swiftly. And that is in case of all medical equipment that can either analyze or support you during the surgery. You cannot just rely on connectivity to the server, or you cannot rely on the bandwidth. You need the decisions on the spot. Last but not least, and a very important factor, is that with Edge AI deployment, the data stays locally directly on your devices. So this is becoming a huge foundation for the so-called privacy by default paradigm. And in that case, you don't need to worry that much about where the data is transferred, because you're just processing the data on the device and send the result instead of the real data.
Yeah, Marcin, if you don't mind, just to add, two, I think, very relevant points here. The first one is, how we've approached AI in the past has really been an evolution of big data. The process was, let's take all of this data, we'll dump it into a data lake, and then at some point in the future, we're going to come back and we're going to make sense of it, and we're going to try to use it for something. We don't know what yet, but we're going to try to use it, because data is, we've heard quotes like, data is the new oil, right? There's value in data, so we want to collect it and we want to store it somewhere and then figure out what to do with it. But the challenge is when we go back and we try to make sense of it, we find out we've got a lot of data that isn't clean, it's not useful, it's not worth keeping, it's not as valuable as maybe we thought, because it's not clean and accurate and actionable. And sometimes by the time we actually do something with it, we've really missed the window of opportunity to leverage it. And that's why we're seeing this trend of real-time analytics and doing things in real time that drives more actionable insights. And we're actually leveraging all of the data that's being generated. So we actually justify having these IoT sensors if we can drive some real-time actionable insight out of it. So that's, I think, one piece that we've seen change on this on the AI journey for a lot of organizations. The other part of it is just access to compute, really bringing AI to the edge. There are a lot of models that run perfectly fine on low power, lower performance compute, but as we've seen with video analytics and IVA solutions, there has been an increasing demand for processing power, which traditionally had to be done in a core data center. And now we're seeing, with just the performance of compute and also the size and form factor of compute being moved closer to the edge, has really opened up a lot of new use cases for organizations.
Thank you, Robert. And couple of examples about edge AI. So definitely the most common use case is all about computer vision and machine vision. As Robert mentioned, on one hand, it's important to collect data and to have some channel to record the data and to store it for later usage. And even if we don't know the use case of the future, the data we're collecting with edge devices might be applicable later on. But there's always a trade-off between how much data you want to collect right now versus how fast and what your capabilities are. And in this example for traffic analytics, we wanted to make the solution really scalable so that the bandwidth does not depend on the number of cameras, and that we can limit a little bit on the bandwidth usage. And then above all, the goal here was to provide real-time AI experience. And in that project, we designed AI model that was initially designed for a cloud system, which was able to take a video as an input and then produce the results about number of persons at the crossroad, bicycles, and actually count number of objects like trams, cars, and so on and so forth. But then we decided to move the model onto the edge. And by edge, we define here as small devices as a simple Raspberry Pi with, back in the days, powered by Intel Movidius chip and simple USB camera and HDMI connectivity so that you can visualize the results. And in that use case, that even that small device was able to analyze the traffic in real time with just a camera. And the biggest advantage of that configuration was that the Raspberry Pi didn't have to store all the data. It was then connected to Microsoft Azure Cloud, where the results of the recognitions were sent, and the advanced analytics, like about the number of people or bicycles and so on, was done in the cloud. Another example would be for retail.
So another good example of IVA, and this is one that Lenovo has been doing some extensive amount of work on, is actually bringing AI and computer vision into the retail environment. And one use case that we've been working on is loss prevention. This is a growing challenge for retailers. One of our customers actually has been evaluating their shrinkage numbers, and they estimate about 40% of their shrinkage comes from scan errors at the self-checkout, up to 40%. If you look at the trend across, we'll just use the US numbers, for example. 2 years ago, it was estimated about $41 billion challenge for retailers and loss from shrinkage. That has been upgraded this year to about $100 billion projection. And the big change here is that we've seen proliferation of self-checkouts, and that has been a key impact on organization shrinkage numbers. With things like the current pandemic that we're facing, we're going to see more automated systems and more things like self-checkouts come into play. And so being able to use computer vision to monitor those and address issues is going to be really important. And this is the excellent use case, one of many that we're seeing of how computer vision applied at the edge can actually really impact the outcome of the business and have a significant impact on cost savings and revenue.
Another example of Edge AI is our product, which we are going to launch later in 2020, called EvaGuard, which stands for Earth, Wind, and Air. It's our joint approach to leverage AI to address some of the humanity's greatest challenges, and in that case, we're training the models to actually detect illegal dumping areas across the world. So with that product, we'll be building a community of people using drones, but actually any mobile device who can either record the videos or take pictures and then upload their whole data to EvaGuard system for further processing, where EvaGuard, as you can see in this example, will then analyze and return the location of, for instance, illegally dumped tires. Here, the very important use case we're working on is about also Edge AI. So imagine a drone just during the recording session can produce huge amounts of data. It's usually counted in tens of gigabytes, and I'm not just talking about highest quality image you can produce with drones. And being able to process the data directly on the drone gives you a huge benefit because the whole solution becomes more usable. Instead of then docking the drone to your laptop or PC and then waiting a significant amount of time until you upload the whole recording or drone's footage onto the cloud to EvaGuard is significant. And then with on-device detection, you can still upload the whole data to EvaGuard, but then drone can actually also reduce the amount of data you will have to download to make EvaGuard usable, just to simple text messages with coordinates. Drones can even trigger alerts when they find something suspicious or something interesting. So yet another use case where you can see a clear benefit of having real-time responsiveness, but actually also to pre-process the data directly on the device and then provide the results almost in real time, rather than waiting for the whole round trip of data between cloud or edge computer. So what is federated learning? Federated learning is about leveraging locally deployed AI models across edge devices. As we talked earlier, back in the days or traditionally, models were deployed in cloud or in data center, and we were sending the data back and forth to get the results. With edge computing, we can actually process the data on the spot, and we can deploy the algorithms really close to where the data is born. Then we call it AI models for edge devices, which really derive the intelligence from the device data. And going forward to the future, you can imagine that all of a sudden we end up with having a number of edge devices having their own local models. They might differ in terms of accuracy, maybe the quality of results, and so on and so forth. So we're asking ourselves the question, would there be a way that we could somehow leverage the models for similar use cases which are produced across a number of edge devices? And we're kind of inspired by the work done by Google back in the days and the early research papers that they produced. So I'm sure that most of you, or if not all, are already familiar with Google keyboard called Gboard, which is about predicting what kind of words or what kind of sequence of words you might use while typing a message for WhatsApp or for your next SMS message. And that actually leverages all the inputs that are happening across the whole Android ecosystem, where Gboard analyzes the inputs from all the users. And then even if you start typing a word you have never typed on your particular device, you might get relevant suggestion about the next word just because someone else did it for you on another device. So why is it important when it comes to federated learning? First of all, it reduces network bandwidth constraints. So imagine a scenario where you don't need to send around the data across your device's infrastructure. You just send the models, not the data. It ensures privacy because with federated learning, what you do, by leveraging AI models across edge devices, I actually mean you train a meta model or you average out all the other models that are deployed on the edge components, and then you produce a new model which you later on redistribute back to your devices as a kind of upgrade. And then better personalization of predictions, meaning that your data and your inputs is taken into account so that you get better results yourself as well.
And Marcin, that's a great example of, we think about federated learning. Many cases, we think it's still something that's farther out as far as when it will be operationalized and in production. But the example with Google using it in the Gboard keyboards is a great example of how it's being used today. Another example from one of our partners, NVIDIA, is they're actually using federated learning in their Clara platform for healthcare. And really the goal is to be able to share the benefit of the collective learning you can do from the different data from different healthcare providers. But in healthcare, you're working with a lot of sensitive data, and there are quite a few constraints, regulatory and privacy constraints that you have to be mindful of. So this allows for shared learning across all of the different data sources. So really interesting how we see this being used, in the real world today, even.
So how it works? byteLAKE and Lenovo have worked together on building a concept federated learning, and we a little bit extended the definition of federated learning from and edge AI. We went beyond just inferencing and introduced local machine learning and actually training happening on the devices. So in that example, we built a set of frameworks which we deployed across a network of Lenovo's tiny devices, which are small PCs you can attach to your edge components in factory or even in healthcare use cases. And then on each device, we had a local machine learning, which was analyzing time series data in steps. And the model was improving itself over time just to reduce the error level. And we're doing so across the network of devices, averaging out the models produced at the edge at the data center level, and then distributing back to the edge devices a tiny update for each model so that we can say that the devices were learning from each other in that particular example. And that led us to building a simulator for predictive maintenance for manufacturing, where we built this simple simulator which consisted of a transparent tube filled out with styrofoam pellets. We attached two fans on both ends and programmed a small device which was more about pushing the styrofoam pellets from left to right, right to left. And we did two types of training. One was happening directly on the device, so analyzing how the pressure inside the tube was changing and trying to predict the best trend about the future values of the internal pressure. And then we also did the federated learning part of it, where we aggregated the models across a number of such simulators and were able to predict more accurately and produce better quality models much faster, when we introduced this collaborative learning and aggregated the numbers from all of the devices. That led us to a filter clogging detector for a factory where you analyze data from a bunch of sensors like humidity, dust level, and so on. And then based on that, you can use mathematical modeling and machine learning to predict how long it will take until your filter gets totally clogged, so that you can plan factory shutdown, for instance, in advance. This is how the simulator looked in reality, and there's a link in top left corner where you can read more about these efforts. And I will play a short video here, and you can review the whole video on YouTube with the link on top, where we actually presented on a number of conferences how federated learning can work in practice. So in that example, as you can see, we attached a number of sensors to the tube so that we can filter out different anomalies and make the model more general, predicting correct values in different scenarios. The important thing here is that we removed the models from the devices. So in that particular example, all of the devices are learning from zero, from scratch. And you see two graphs here, the green one and the blue one. The green one is based on real-time predictions or on real-time values from captured from the sensors attached to the tube. And in that case, we're visualizing how the air pressure is changing within the tube. And the blue one is a prediction. As you can see, we enabled federated learning, and almost from time zero, you're getting the correct trend as long as the air pressure changes are happening. But as we switch to the standalone version, you see that the predictions are not that good, and actually even the trend is wrong, right? I'm not talking about the absolute values. And then we trained the model until we got the accuracy for federated learning at the level of 95 to 98%. And at the same time, the standalone version reached only about 40% of accuracy. And so that leads us to a number of benefits you get with federated learning. And some of them are inherited directly from the edge AI deployment. And I'm talking about enables scalability, solves low throughput and high latency challenges, because you just send the model or the delta model instead of the raw data, improves accuracy. At least you get faster, better results. You can leverage your models across the network. But one of the biggest benefits here is probably privacy. And as Robert mentioned, for the healthcare, it's becoming more and more important there. And also for telecom, we've been working on some use cases there as well, where privacy becomes a key, like a factor for federated learning. Just because you don't need to share the data across the devices, you can just share the models. So imagine medical practices, just providing the models to other sometimes competitive medical practices, and then everyone retrains their models using internal data and models from competitors, and then collectively you all get better predictions and better results. By the way, we wrote this white paper about federated learning, which you can download from both byteLAKE's and Lenovo websites. And the link is in the bottom right corner.
In closing, if you have any more questions about what Lenovo is doing in artificial intelligence or what byteLAKE's doing, please feel free to reach out to either of us or visit our website, bytelake.com or lenovo.com/AI. Thanks, everyone.
Thank you very much.